Brendon. We're doing lab 4, part 1. So you can see that we're doing the stepper motor controller. So this is the stepping sequence. Yes. You can see, okay. So then we have EN is enable stepping. So if 0, you'll be stopped. Then if 1, you'll be controlled by the clock lah. Then CW is 1, it'll be clockwise, 0 will be anti-clockwise, okay? So then therefore we created the state diagram. You see this? Yeah. So you can see also that this is the legend here. Okay, so now you want to fill in the table, right? So you look at here, the S0, okay. Let's say the output. So look here. So output, so this is a 1 0 0 0 0. So see 1 0 0 0. So for S1, how about S1? 0 0 1 0. So 0 0 1 0. How about S2? 0 1 0 0. 0 1 0 0. How about S3? 0 0 0 1 0 0 0 1. Okay, then we look at how about the next state. Next state so we look at the, so since the EN is all 1 for all the steps here, see 1 1, so we just look at the CW. So clockwise is 0, so therefore
clockwise is 1.
No, it's 0 here. 0 here. So yeah, it means CW means clockwise. So 0 means anti-clockwise. So we refer here. So we are at S0. So the previous state says S3. So S3 here. And then since it's 1 means it's falling clockwise. So this way. So therefore you go in the next state. So from S0 to S1. So for here also the same thing. For S1, so previous one be S0. So this one is 1. So S2 the next step. And this one for S2, previous one be S1. Next one will be S3. S3, so you have 0 here. Previous state S2, 1. Next state is a 0. Okay, so then we get the JB, KB, JA, KA from here, based on this table.
Yes.
Okay, then we fill in the Carnot map, and then we find out the equation for JB. So JB equals to A EN CW plus A bar EN CW bar. Then KB equals to EN A EN CW plus A bar EN CW bar. And then JA equals to EN, whereas KA equals to EN. So our output function we got for 0 0 is O0 will be A bar B bar, and for O1 it will be B A bar, O2 will be B bar A, and then for O3 it will be AB. Okay, so this is our circuit. First we look at here first. Okay, so we created our schematic already. Okay, so now moving on to the circuit. So we set it at 20 Hertz because the other frequency will cause some malfunction. So this is the perfect one, and the speed is also good. So you can see that this is the EN. So if I stop it, it'll stop. Yep. So if I enable it, then it will continue to spin. Okay, so let's enable it. Okay, 1 2 3. Okay, so let's look at this part. This is the CW. So since it's on now, it's high, so you can see that it's clockwise. You see? Okay, how about if I disable it?
Yeah, moving
anti-clockwise. Therefore, it shows the stepper module. Yeah. So we're done. Thank you.
Alright, thank you. Hi guys, I'm Cheng. We're doing lab 4 of part 2A, which is the state diagram. Basically, we construct the diagram based on we constructed this circuit based on the state diagram. This is the register, and this is the XOR. Basically, we need to follow this. So, yeah, pretty much we follow the datasheet of the register. We use this for this. Q0 will be X2 will be Q0, which is 3, and X1 will be Q1, which is 4, and X0 will be Q2, which is 5. So what is your X3? It will be D1.
Okay.
Alright.
Okay, you show the state diagram, right?
Yes. 0 0 0, it will always be infinity until you change the state. And then how do we do it? So what I do is this one is 0. So the switch,
toggle lah.
Yeah, this is toggle. So I press 1, it will send one signal to here and to here. So it will start the system. 1 0 0, it will go infinity. Right, and this is yeah.
So you can see it's now 0 0 0, right?
Yeah, we construct the diagram. Alright, now proof our concept.
Okay. Toggle it. Right, leave it on. Okay.
Alright. You see it follows perfectly. Okay, 100, 010, 101, 110, 111, then 011, 001, and back to 100. Alright.
Okay.
Now let's increase the speed.
Okay.
Alright, we need to make sure that it's actually random, so we just increase the speed even more. As you can see, it's actually very random.
Yeah.
Alright. And now we want to set it back to 000. So how do you do it again? We just set, we purposely press 1 here because for XOR gate, 1 double 1 input is, and the output is 0. Alright, now test. You cycle first. Alright, 0. I'm too slow.
Okay.
Alright, now it becomes 000. Alright.
Okay, thank you.
Thank you. Alright, so this is part 2 of lab 4. Yeah, alright. Basically, we are supposed to generate a random value. Alright, 010, 101, 110, 111, 011, 001, 100, and finally 010. Actually, it's a loop. Basically, at beginning is 000. So what I do is, I take out the, I ground this D1 and D2, and we will reset the system and it will start running. So this one D2 is D1 and D2, pin 1 and pin 2. Yeah, D2 is VCC. For D1, which is the output of this is X3, and X2 we are not used. X2 we are not used, and this is where we connect to oscilloscope. X1 is connected to the pin of the pin 1 of XOR. Yeah.
XOR.
Yes. And then Q2 is connected to the pin 2 of XOR. So our file is ground because we want to set it to a random generator. If we didn't, if we say the same, it wouldn't work. It's XOR gate.
Okay.
Alright. 0 is 0. So it start running infinitely, and look at that. The value generated is actually very random. But if you look carefully, it's actually the same. This is
not zoom in. Yeah. There we go. Because you want to compare it.
Yeah, basically this is pseudo random number, and this is output. This is our input, and output is a pseudo random number. Alright, now we'll go to the next part. For now. Alright, so basically we move the 2 here.
For the second part, right? You show the.
Yeah, for the second part, x7 equal to x3, XOR x0. Alright, this is x7, this is x3, and x0. Yep. Basically we move from 3 to 5, and then from 4 to 5, and then from 5 to 10. Alright. Now you can see, yeah, it's the same circuit. It's still random,
okay,
but it changed a bit. This will be a bit longer, this will be shorter. Alright, and that's all.
Then doing part 3, and then this is our state diagram that we designed. So this is the table. Okay, and then from the table we design the K map, and then we get the result. So it's DA equals to BW, DB equals to W naught, and then F equals to AW. And then from that we use De Morgan's theorem to obtain the different type of equation. Okay, then we design. So you can see that W is connected to here. So W is from the previous one. So we use this one, right? Yeah. Okay, then so now
X naught.
So now you can see here, we already combined them together. So then now we look at here, the results. So you can see it's a random number. So you can see there's so it's 0, 1, 1. So there is the sequence, you see. So it's the sequence 0, 1, 1. Okay, so you can see that at 0, 1, 1, then there's 1, 0, 1, 1, 1. And then there's this spike over here. So this is the false output in between the clocks. So this is because of the transition in the input from 1 to 0. So because milling machine is asynchronous, so therefore when the input change, the output also change at the same time according to the logic. So this will have some glitches inside the
machine.
So therefore you get this kind of spikes.
Alright.
Okay, thank you.